Before we start, I would like to take a moment to recognize the traditional Indigenous lands where Eco-Canada's office is based in Calgary. At Eco-Canada, we're committed to working towards respectful acknowledgement, collaboration, and reconciliation with Indigenous peoples across Canada. This starts with acknowledging our honour and privilege to live and work within the Treaty 7 territory. Today we are presenting from the City of Calgary, home to the Métis Nation of Alberta Districts 5 and 6. We would also like to take this time to acknowledge the traditional territories and oral practices of the NECB, home of the Blackfoot Confederacy, which includes the Siksika, the Piikani, the Kainai First Nations, and the Tsuut'ina and Goodstoney, which include Chiniki, Bearspaw, and Wesley First Nations.
Beyond compliance, leveraging energy codes to deliver better buildings. Just first, a little bit about myself. I'm a mechanical engineer with 20 years of experience. The first 10 years of my career, I operated I practiced as an HVAC and plumbing design engineer. When the energy codes emerged as a matter of code in 2016, having had been in the mechanical segment, which up until that point was kind of the go-to all-purpose for all things energy, I saw an opportunity there and moved into specialization on the energy side of things. And since then, with our small team of 5 that I lead, we've completed about 2,000 Part 3 building and Part 9 energy code compliance, mostly new construction, but existing building projects, energy audits as well. I'm registered in the 3 Western provinces, intermittently registered in Manitoba as well, but just not quite at the moment. And just a bit of our Enforma's MO here before we get into the content. Like I said, if it's energy and it's in an area that we practice, we pretty much we do it. We're always happy to field questions from colleagues, builders, owners, and our approach is that your objective is our objective, whether that's a very aggressive energy target or just getting across the goal line. So what are we going to be speaking about here today? So actually, maybe Haley, if you have a chance to put up that first poll, if it's possible, so we can kind of get a little bit of a sense of who is in the audience. I'll go through the agenda here. What's so great about energy codes? So for some participants here, I'm already seeing there's a good number of energy consultants. Some of this is going to be old news for you, but what I'm hoping that we can pull out here is the merits of employing energy codes as a design strategy. And so for whether it's the seasoned building design professional or energy consultants for whom this will be second nature for, my hope is that we can still highlight the advantages of that energy codes bring to the design process, because it's always up to us as the design team to actually to seize those opportunities. Okay, so what we got here, I'm just taking a look at the poll. Okay, that's a pretty good mix. More energy consultant heavy here than I anticipated. So look forward to maybe some technical questions towards the end. So what's so great about energy codes? That's going to be our focus. I'm going to do a brief overview of the application of the energy codes, but then the focus is going to be 9.36 and 9.36 in its sort of core original edition. There's been some modifications and some changes coming in the national edition, but because in part this is for an audience with not high exposure to the energy codes, the intent was just sort of give the general framework and again underscore to everyone how energy codes can be employed to achieve a better building result at the end. So we'll talk about the key structures there, the modes of demonstrating compliance, the prescriptive and the performance path, and then at the end we'll sort of tie it back with a discussion about performance verification and in some enhanced energy efficiency strategies. Okay. So what do energy codes address? Well, unsurprisingly, they address basically all of the components of a building system that contribute to energy consumption. I've got an old pie chart here from a Natural Resources Canada document. This is a breakdown of at least up until 2010. Things might have skewed somewhat since then, about the energy consumption breakdown for residential consumption in Canada. Unsurprisingly, with Canada being a cold climate, we've got a heavy tilt towards space heating and water heating. There are no energy codes that are in routine application actually apply to appliances. We can see, though, that is a sizable energy component. It's only the National Energy Code for buildings between 936 and the NECB that applies to lighting, but energy codes are always interested in space heating, water heating, and space cooling. And so they're always going to be addressing the building shell, the building envelope, the thermal insulation parameters, the space heating and cooling appliances equipment, and the domestic hot water heating. So this slide is sort of reflects the crux of what we're trying to talk about here. And so why are energy codes a big deal? I mean, biased from an energy consultant perspective, but when employed with intent, they're like the gravitational force that pulls the different disciplines together. Because energy, we just discussed from the last slide, energy consumption is influenced by the whole range of aspects in a building. If we're trying to achieve a particular end result or a particular performance, that's necessarily going to require collaboration and conversation, ideally at the front end, to ensure that the project is on track to hit those targets from the beginning. So in short, energy codes certainly can, and ideally do, drive an integrated design process. So here's a slide that's basically, highlights from the experts, just reinforcing that point. This is a little excerpt taken from the American Institute of Architects, where they're contrasting sort of the benefits or the absence of benefits if we don't take an integrated design approach. I mean, I think this is probably a pretty straightforward concept, but really it does make a difference. And the reality is that an integrated design process is just not always employed. Key advantages on this integrated design list that I would point to would be decisions influenced by a broad team. So even if we have an orientation towards high energy efficiency, let's say we're totally convinced that heat pumps are a great application for a building, they reduce overall energy consumption, we still don't want to be making determinations or design decisions about that system in a vacuum. This image here does a good job of sort of pulling out the different facets and makes it a little easier to see how they would correspond. If a house is planning to put some solar PV on there, well, how much of the annual energy do we want that solar array to produce, to be responsible for, to generate? Well, that depends on the overall building envelope's thermal insulation. And then, even if we've got a great technology like heat pumps, it is the case often that some of this more advanced technology is more design parameter sensitive. Heat pumps, for example, air source heat pumps, they do have reduced output capacity during periods of colder weather. They generally have less overall heat capacity than, say, a furnace. So their sizing ought to be taken into consideration with the building as a whole. Okay, so before we get into the discussion that we're going to focus on 936, I thought I would just give a broad 30,000 foot level of what's out there. 9.36 energy efficiency is certainly not the only energy game in town. for buildings that do not fall under Part 9, which I'll discuss what that means here in a second. By default, typically in most of Canada, the building would be then called a Part 3 building and would be subject to the National Energy Code for buildings. In British Columbia, they have another couple of standards. ASHRAE 90.1, an American standard, that's the American Society of Heating, Refrigeration, and Air Conditioning Engineers. They have a standard that's widely adopted throughout the United States, which they provide as an option for compliance for certain buildings. And then there's the BC Energy Step Code. That's an enhancement of the model national codes that BC has taken upon itself on both the Part 9 and the Part 3 side that modifies and makes, I would say, more stringent some of the targets there. We're just going to focus on Part 9 so that, again, for that maybe more simplistic overview of energy codes, and I would say the most prevalent application as well. What I can say though about the BC Energy Step Code that does, I would say, underscore the key messaging here is that as we've seen, over the last 5 to 7 years, as Step Code has become widely adopted and now codified in BC, there's been an organic transition from a more siloed design approach to a much more organically driven collaborative approach, and it's been great to see. It doesn't. My thought would be it doesn't have to take difficult energy targets for a design team to make the decision to move towards that more collaborative, heavy, front-ended, integrated design approach. But it's certainly it's a practical necessity as the energy targets get more difficult, and it's been nice to see, because I think, what aside from the fact that it's codified and it's a requirement, I think it is leading to better design practice overall. So that's kind of the high level. Now we'll jump into the focus here on 9.36 energy efficiency. So again, I know all you energy consultants out there, this is all, you've known this for a long time. For those who maybe don't have as much exposure to the code, the model national codes, which for the most part are then adopted at the provincial level with some adaptation, it's divided into a bunch of parts. There's a part that designates the occupancy classes, fire protection requirements, structural requirements, and then I think it is in fact the largest part, or binder section if you have the hard copy, is Part 9, which is small housing in small buildings. And while in absolute quantity, numbers of buildings, we can safely say that most buildings would be Part 9 buildings. So on the image here on the left, you can see exactly what that contains. So residential occupancies, single family detached, stacked, small apartments, but even some small business buildings, even medium and low hazard industrial occupancies, all of which, to fall under Part 9, must have a building area of 600 square meters or less. That's as viewed in plan or from space, and must be 3 stories or less, not including a basement. So that's 600 square meters. If you had a 3-story building, you could have up to 1,800 square meters of gross floor area, but that footprint has to be 600 or less. Okay, so now we know what buildings fall under Part 9.36. So as I was saying, the Part 9 is where they jumble all of the requirements for a particular kind of building into one part. That would include, so there's a section there on ventilation, there's a section there on structural requirements, crawl spaces, all the things that fall under Part 9. Well, Section 36 of Part 9 is energy efficiency. So just to give a high level of the structure of Section 9.36, the first subsection talks about what we just talked about, what kind of buildings does this apply to, and how do we demonstrate compliance. And then the next 4 sections are about the modes of compliance. So this modes of compliance that I'm going to discuss here next, this really is almost universally true, regardless of what energy code we're talking about, except for, I mentioned the step code, that those work more on an energy budget, like depending on what kind of building you have. They'll say you're basically giving an energy allowance per square foot. But for the most part, most energy codes, including the NECB, ASHRAE 90.1, you can say they generally offer these 2 modes of compliance: a prescriptive path and a performance path. And I'll get into what those 2 things mean. So a prescriptive is, and I'll be reiterating this point in a subsequent slide. Prescriptive is, think like prescription. You go to see the doctor, he gives a prescription. The pharmacist just adheres to the prescription, make sure that it's followed to a T. Whereas performance path, it involves energy modeling. It's a different way of demonstrating your compliance. So before we get into some of the specifics of the prescriptive path, there's some key principles or some fundamental requirements that apply to both methods. And so this is where again, keeping in mind that the core message here is leveraging energy codes as a means to better buildings through the process of integrated design. What I think needs to be conceded is that the prescriptive method is maybe the most simplistic, but also doesn't sort of force that collaboration or that coordination quite as much as the performance path or the energy modeling path. But that doesn't mean that we can't pull out some key aspects to get those benefits of for a better building. And so these couple key principles that I'll be discussing here, namely continuity of insulation and continuity of air barrier, those would apply. So regardless of whether we're using the prescriptive path or the performance path, 9.36 introduced a requirement where, unless quantified otherwise using the performance path, it is a necessity that your thermal boundary must be maintained throughout all junctions. And so when the codes came out in 2016, we started to see the municipalities focusing a lot more on these sort of details. And what all we're trying to see here is, if you see this as a foundation wall for a basement, we've got the interior framed wall insulated, comes up over the lip of the foundation, the floor header, the rim joist, and then here's the above grade wall. When you hear that terminology, continuity of insulation, when the codes were first coming out, it was a frequent thing. Builders are like, what the heck are they looking for here? Why are they saying my details aren't adequate? I will say that sometimes it remains not 100% clear what a given plans examiner might be looking for specifically. Ask if we don't know. But generically speaking, when we hear continuity, when as a design target or as a request of evidence from a planning group, when we hear the words continuity of insulation, ultimately they're looking for details that show how we're going to maintain uninterrupted insulation. And when I say uninterrupted insulation, I mean, look, the floor sheeting here interrupts that, but we mean without a substantial break in the insulation. The second core principle, which definitely applies to both the prescriptive and the performance, is continuity of air barrier. actually, I didn't know this until some time ago, but ASHRAE 90.1, that American standard that's been in place for a long time, one of their requirements is actually a drawing package that has a red line section where the designer has to demonstrate how their air barrier is being maintained. And so, I mean, air barriers is its own conversation. There's different kinds of air barriers. There's exterior air barriers, there's interior air barriers. Sometimes your interior air barrier is also your vapor barrier. But the point is, when we have this exercise from the beginning, it forces us to examine and really plan our details of how we're putting something together. So, I can say I don't think there was ever this much focus on air barriers before energy codes were widely adopted. We know that air tightness is a very substantial contributor to energy consumption, and so this is definitely, a facet of the energy codes that lead us to better buildings. So now we'll talk about the structure. Whether we're talking about the modeling rules or the prescriptive requirements, 9.30, the requirements of 9.36, you can say are organized generally in terms of heating degree days, or for simpler terms, maybe the coldness of the location. So maybe no one, if anyone ever wondered what a heating degree day was, well, it's the middle of summer right now, so it's probably above 18 Celsius in most places where people are watching. But let's just say it's the average temperature today was 0. So 18 Celsius is the presumed indoor temperature. 18 minus the average 0 is 18. That would be the number of heating degree day points, if you want to think about that from today. And then they add that up for on an annual basis, on a per location basis, based on their climate. And then you get bands. So climate zone 4, for example, is anything that's less than 3,000. 5 is 3,000 to 4,000, and it generally goes up in 1,000 heating degree day bands. The higher the number, the colder the climate, and in correspond with the colder the climate, more thermal resistance is more higher levels of insulation are required or employed as the reference target for the energy modeling. So while I don't know how new some of these concepts might be, if they're new, that's at the end of the day, they honestly are straightforward. We're talking about following along to make sure thermal insulation is continuous, that your air barrier is continuous. I would say if we're going to be taking the more simplified approach, the prescriptive approach, there's only one sort of little math component here, and that is that the thermal requirements that we'll be identifying here, the code is always speaking about effective thermal resistance. So in this example here, if the probably the most standard wall in conventional wood frame construction would be a 2x6 stick frame R20 wall. Well, in reality, that wall doesn't perform at R20. It performs at something closer to 15.8 for a couple of reasons. As soon as we take that 6-inch bad insulation and squish it a bit so that it fits into a 5.5-inch cavity, it goes from R20 to R19. But like this image kind of nicely shows, there's going to be two different pathways for the heat to flow out. One is going to be through the wood framing member, one's going to be across the batt insulation. And compared to the batt insulation, the wood is a much quicker route, or a path of least resistance, what we call a thermal bridge. And so we have to account for that. It's not a, this is the equation. For the most part, we're just adding up the thermal resistance of the components in the assembly, with the exception of a parallel resistance calculation for how we sort of area weight average the effects of the cavity insulation and the wood frame. So this is something that often, probably most builders would lean into the support of an energy advisor or an energy consultant, whether for the prescriptive path or the performance. But I would say, genuine, this is not rocket science, and if and is pretty much the full scope of the math, for anyone who would find this to be intimidating. There is quite a bit of resources there in the appendix to help walk you through those calculations. And so I had the example there of the wood frame wall assembly, but this same principle would apply to any opaque envelope assembly that would have some framing members in it, which is to say a layer where there is two different materials. And so we have to account for how the heat flows through them on average. Okay, so now that we've kind of built the framework of the universally governing principles or requirements for both the prescriptive path and the performance path, we're going to focus in on, okay, what does it mean? What does it mean if we take the prescriptive path? Well, I already outlined sort of my canned anecdote about the doctor and the pharmacist. So that's true. Again, prescriptive compliance is essentially a checkbox activity for everything that the code says that you have to do. You got to check, make sure that it's done, and that does include preparing some calculations to show that your envelope assemblies meet the RSI targets that we'll be kind of cruising by here in a minute. I would say that you could characterize the prescriptive path as being rigorous but straightforward. So depending on the specifics of your project, there could be any number, a dozen or more requirements that you have to check. The performance requirements of the HVAC equipment, calculating all of your thermal assemblies, but it is straightforward. There's no, at the end of the day, it's as long as you do all the things, then you're compliant. Okay. And so now we're going to just dive into, or I would say dive into, we're going to give sort of a broad look at what sorts of requirements are imposed using the prescriptive method. So here's a couple tables here. Effective thermal resistance of above ground opaque assemblies. If you recall, remember I was talking about the climate zones. So we've got these different RSI. Oh, and by the way, so R value is imperial. When we, everybody's heard an R20 bat insulation. Well, in RSI, that's 3.52. So when they're interchangeable, there's just a conversion factor. We live in Canada. This is metric. So all of these tabulated values here are RSI. You can see as we go across the climate zones, we go from warmer to colder. For certain components, we can get quite a wide range of requirements. I don't know if most of the people are in Alberta. Most of Alberta is 7A, climate zone 7A, with 7B being for the northern region, very southern Alberta being zone 6. So ceilings below attics in a house without a heat recovery ventilator would be an RSI of 10.43. That's very nearly R60. And if the building does possess a heat recovery ventilator, that insulation value is reduced to 8.67. And with many of the different details, there are some prescriptive requirements that again identify particular details that must be adhered to. This one here is showing that over the exterior wall at the heel of the truss, you have to maintain a minimum of RSI 3.52 or R20, and that would be to avoid ice damming. So just a little construction detour here and a little polling check-in. Since I mentioned in that last slide that there was two different insulation requirements, depending on whether the home possessed an HRV or not. Haley, can we put up that slide about the HRVs? I know you energy consultants are probably going to be very familiar and love them. Maybe a few of the can't stand them, sir. Oh, okay. I'm glad we've got at least a couple of attendees who've wondered what they are. That's great. Okay, so and you know what? I didn't put it on there, but there's HRVs and ERVs. So maybe even there's something for the seasoned consultant to learn. HRV stands for heat recovery ventilator. ERV stands for energy recovery ventilator. You're like, well, I thought heat was energy. Well, the distinction between the two is that when we say energy, we're including the latent heat, which is to say moisture, the energy that the moisture in the air carries. So maybe I'll explain first what this box is. So Canada is generally a cold place, right? Hopefully we've all accepted that. The outside temperature is generally colder than on the inside. So, and we need to have good indoor air quality, right? So we always need to be bringing in fresh air, or regularly, if not continuously, bringing in fresh air to make sure we maintain good indoor air quality. Well, this clever little box takes advantage of the fact, okay, we've got an ongoing incoming air load that is generally cold air, and we have to have an air balance, so we have to simultaneously have outgoing air. Well, since that incoming air is generally colder than the outgoing air, why don't we use some of the heat of the outgoing air to heat up the incoming air? And that's all these boxes are. If this little well, I guess on its side it's a diamond, it's kind of like a cube. You've got air passing in two different directions. All these things are, if you can imagine, corrugated plastic layered this way, one on this way, back and forth on the other, and that structuring of this exchange, it is a heat exchanger core, allows for the two air streams to be passing next to each other without being in direct contact through those channels created by the 90-degree switched corrugated plastic layers of the heat exchanger. And there you go. It's just a heat exchanger. It's nothing more than a heat exchanger. And well, it's not nothing more. It's also a box that whenever it's on, we know that it should, if commissioned properly, is delivering a proper amount of ventilation air to our house or our space. And then there are some designs, the ERVs, that allow, so this core here would only allow for sensible heat transfer, so that's just temperature. But there are energy recovery ventilators that allow for extraction of the heat from the moisture as well. Generally, you need something that's moving the moisture between the two air streams. So I hope if there's questions on that, probably went on a little longer about that box, but I like to identify that one because no need to be embarrassed. I encounter people routinely who are even building and still don't fully understand what the HRV is for. So that's it. So back to the prescriptive requirements. Just like the thermal insulation for the roof and the walls, there's specific requirements for the windows and doors. Windows and doors are generally expressed in terms of U value, which for whatever reason is just the inverse of R value, or metric RSI, USI. More R value is better, lower U value is better. They're the inverse of each other. Yeah. Again, with the prescriptive path, with this checklist activity, we've got HVAC equipment, we've got hot water heating equipment, which again needs to meet the requirements of the tables, whether that's undertaken by yourself or prepared by an energy consultant. It remains that checklist activity. And I will say that the municipalities have generally made that they're pretty accommodating in making that exercise relatively painless, which is to say you don't have to invent your own paperwork for the most part. Most municipalities have forms that you can fill out. You have to know how, of course. And I would say if there's any, well, I know there's some, if some of the municipality or First Nation representatives here have not yet implemented the 9.36, I've definitely seen some municipalities borrow the forms or base it on templates from their neighboring facilities. There's no need to reinvent the wheel. So hopefully I've done a reasonable job of conveying to you the fundamental mode of compliance for the prescriptive path. That's one of the two main approaches to demonstrating energy compliance. And as I said, just to recap, because we're trying to convey how this can be used as a strategy to build better buildings, even though it is a check, in no small part, a checklist activity, and can be undertaken in sort of a siloed approach. All the better if we still have those conversations for across discipline for the unavoidably and truly overlapping aspects such as the insulation, continuity of the air barrier, mechanical design, and the like. So, but now we'll move into the second mode, performance path. So this has a different structure. I've got a little snippet there. We generally use a software called Virtual Environment. That's because we use it heavily on the Part 3 buildings. For Part 9 buildings, actually, HOT 2000 software made by Enercan would be a far more widely used software. Certainly, I think what probably all of the certified energy advisors are using. But regardless of what software you're using, performance path entails the same methodology. Instead of it being that checklist activity where we verify that everything on the list has been attained, following the rules from, in this case, 9.36.5, the portion of the section that outlines all the rules for the energy modeling, it tells us how, based on what we want to build, that we build an energy benchmark for that building. And so long as we outperform, which is to say use less energy than that benchmark, then our building has demonstrated compliance. What are some of the advantages of this approach? Well, it provides more design flexibility. I would also say it is even more so of a collaborative tool, because in contrast to the prescriptive path, where at the end of the day you get a checklist, with the performance path you get some sense in quantified terms of how much energy the building is going to be using relative to the benchmark. And but beyond that, some of the prescriptive requirements, one of them that comes to mind would be slab insulation details. One of the boxes that we have to make sure that we check when we're using the checklist approach, if we use the performance path, because it's concerned with the building's overall energy consumption, so long as we can quantify properly any deviations from the prescriptive path, we can tune our design. So let's say that slab insulation was just, for whatever reason, going to be a terribly cost burdenous component for a project for whatever reason. Because slab insulation, or the lack of it, can be properly modeled in a model, you could potentially modeling it out. Now, you could take it out if your model showed that the proposed design was still as or use the same amount of energy or less than the reference case. Now, to be clear, I'm not advocating for eliminating insulation, but certainly design flexibility and even marginal cost savings has been one of the key drivers of using this approach. But the quantification is definitely an advantage too. And what I'll say is that so we're in the jurisdictions that we're operating in. There's quite a number of rebates and incentives. No doubt, many here are familiar with the ongoing CMHC programs promoting multifamily construction, a program called MLI Select. Almost all of those programs are requiring an energy modeling based approach so that we can properly quantify, relative to a benchmark, how energy efficient our end result is. Okay, and that's aside from the fact that it is also a requirement in some jurisdictions, pointing back to the step code there, the approach that they're taking there intrinsically requires energy modeling. And okay, so this is actually the last slide. Before we'll take some questions here. Haley, you can put up the question about airtightness. I definitely know all the energy advisors are very familiar with airtightness testing. I mentioned what this is meant to just touch upon is, I guess, the advantage of the performance path and sort of the whole building approach that it enables. So in the energy model, one of the assumptions that we have to make is how leaky or how airtight, if you want to put a positive spin, a negative spin on it, is the building. So, but one of the ongoing criticisms about energy modeling is, how do you know that it reflects anything like the real world? And that's a fair criticism. You can build the most energy efficient home, and if we leave the windows open all throughout the winter year, well, we're probably not going to attain the predicted energy performance that we had hoped for. But occupant behavior is not something we can control. We can only control the things that we build. And one of those things is the airtightness of the building. So what you're seeing here is what we call a blower door fan assembly. Retrotech's probably the most common make that's used here in Canada. Anyways, at the end of the day, we install this canvas, this red cloth with a frame, and we put a fan across that membrane, if you want to call it that, and we can do one or both of positively pressurize the house or negatively depressurize the house. And there are specifics of different procedures or protocols that we have to follow, but the overall objective is simply to measure how much air do we have to be moving, how much air does this fan have to be moving to sustain a particular building set point pressurization. And so from that, we were able to compare apples to apples about how leaky or how airtight is this building. And when it comes to, like I said, these incentive programs or these more advanced energy codes, they're actually asking for us to take those airtightness test results and plug them back into the energy model to see a couple of things. Number one, well, did we maintain our target? But also sometimes as a means of demonstrating that we well exceeded the target. And so airtightness, while that's a conversation of its own, it certainly kind of rounds out the high level of this integrated design process and some of the merits and the strategies that we can employ when using a performance path-based mode of compliance. So glad despite the late start, I was able to get through all the slides there. I don't know if we're going to go a little bit long because we started short, but Haley, I guess if there's questions, I hope and still time, we'll be glad to move to that now.
Definitely. Thanks so much, Mikhail. We have a few questions. The first
Mhm.
one is, since everything here is based on standard, well-established codes, and considering the high interaction between different systems in a building, could AI be easily used both to design efficient buildings and to predict accurately both energy consumption and the whole efficiency management of buildings?
Well, I think the short answer to that question is almost certainly. I definitely, as an energy consultant, I'm paying attention to the AI space very closely and trying to, as much as possible, integrate AI support for the tasks that we use, the analysis that we do. What I will say is that I think the closer that we get to real world tasks. Like I think it's quite a long time from now before we have robots showing up and doing air tightness tests. I think I hope, quite a bit of time left where the human component of a building design, how much money do we want to spend, those human factors um, keep uh, keep us employed and keep the real person involved. But to the degree that once those decisions are made, is there could a lot of the analysis be wrote and be undertaken by AI, even on the existing building analysis? For sure. So
Thank
I don't
you.
know. Yeah, I don't know if hopefully that answered the question. It was a kind of
Yeah,
a broad one. Yeah.
a few more questions we can get through quickly. With bath exhaust, dryer exhaust, and kitchen hood exhaust, how does HRV, ERV fit?
Sure. That's a really good question. So as as we have moved away from, I don't even know if you, well, no, you can get at least replacement gas-fired hot water tanks. You can still get what are called natural draft gas appliances, where it's still relying on the buoyancy of air to help pull the products of combustion outside of the space. One of the key code concerns always from both the energy perspective and the mechanical perspective is that if you have any natural draft gas appliances, you never want to have a severely negative depressurization in the house or the building, because you could actually downdraft those products of combustion, which is a health and safety risk. Okay, but for the most part, so new construction is pretty much what we call all separated combustion gas-fired appliances, where they've got a powered fan that brings in the fresh air to help the fuel combust, and then it's a closed path that interacts with whatever it's heating just via a heat exchanger, which is to say that from a safety perspective, it's not near the concern that it used to be. So we're not it's not maybe a health and safety risk as much anymore. However, no, an HRV or an ERV typically is only sized to meet the ventilation load of the building, and then it is it is, and I think there used to be something in the Alberta Building Code that had a threshold for, if you have a certain sized kitchen exhaust, they might require you to have a makeup air dedicated to that exhaust hood, which is to say when you turn on the exhaust fan, you got to have something, a fan or an opening in the house, opening up to allow that air to move through the house. Uh, it's not a great idea to have sustained negative pressurization in a building. That just means we're drawing air through the building envelope. It's coming through in an uncontrolled manner. It could be going by some pipes, but you know, generally speaking, if we're talking about a range hood that's like 150 CFM and it's not being used for that long, maybe crack a window. I would say it's probably not a serious threat to the resilience or longevity of your building envelope. And with the transition to separated combustion gas-fired appliances, it's it's unlikely to be a health and safety concern for most, if not all, new construction.
Awesome. Thank you so much, Mikhael. That's all we have time for today. Thank you everyone for coming, and thank you, Mikhael, for your time and giving this presentation. Very informative. Have a great rest of your day, everybody.
Thanks, everyone.